light spectrum. And I think we talked about, usually we don't give frequency. We'll get into fiber optics. So different type of cables are designed to handle different frequencies of light. But when they specify the frequency of light it can handle, they don't give it in frequency, they give it in wavelength. Okay. Fiber optic. Right. So copper, normally we don't rate copper at a frequency unless it's a communication cable. So power cables, they're not rated in a frequency because the power cables are designed to either handle DC or 60 cycle AC. So, because that's what power is here in the United States, or 60 hertz. We have two predominant frequencies used to transmit power. We have 60 hertz and 50 hertz. And they're, European and some, like I think Africa, some countries are split depending on where you're at. So some of them is 50, some of them 60. So it all depends, where you're at. But over here in the continental United States and also Canada and Mexico, we use 60 cycles. And then of course even 60 and 50, the frequencies are so close and you still don't compensate for conductors. Now your transformers will be a little different. They have to be wound a little different to get the same level of voltage when you go through a transformer. So transformers will be a little different. Motors over there, depends on where they're at, they'll run at a little slower speed than they'll run over here. They'll run at exactly the same speed. There's just such a slight little different. Usually we just ignore that. So when we get into the light spectrum, or even into real high frequencies, instead of talking about terahertz and gigahertz and that kind of stuff, normally what we do is we go into wavelength. So 60 cycles would have a wavelength. It would just be a real long wavelength compared to other frequencies. And basically what it is wavelength is compared to the speed of light in a vacuum. Very high frequencies are usually given as wavelength instead of hertz. Every repetition of electromagnetic wave moving through a media has a length referred to as the wavelength. Does that make sense? It's determined by the frequency of the wave to the speed of light. So the reference is the speed of light. So here's the little formula right here. So wavelength, we use the Greek symbol for lambda to represent wavelength, would be the speed of light divided by the frequency that you want to go to. And then we multiply that times 9, and then that's going to be nanometers. And so normally the light spectrum is in the nanometer range. And what has become important is that different fiber optic cables is going to be rated in size. We'll talk about that later. It's going to be core size, cladding size. It's going to be, and also going to be rated in the frequency of light that it's designed to reliably carry. And we usually start in it's usually in the infrared or red range. Right in there is predominant colors that we use in light or in fiber optic cable. So there's several things that we'll look at, but when they give the light speed, they don't give it in frequency, they give it in what? They give it in nanometers. And we'll look at that when we get into more detail. Like this is just a basic look at fiber. Refraction, I think we looked at this, and this is what makes fiber work. And it's really, really neat. Did I show you the video on refraction and reflection? Let's see if it's on here. It's probably up there. But it's a pretty neat video. And that should be in the fiber section, so it's probably over here. Oh, everything's supposed to be here. I don't know what's going on with my videos. There ain't hardly any in there. But what we'll do is we'll just, like you said, there's tons of them on YouTube. I thought I was in YouTube. I guess I was.
There it is.
This is the one I wanted to do. So what we're doing is we're passing this to glass, and then we're going to make it come out and go back into air. Okay. So you notice when it comes straight in, it goes through, but as soon as he starts spinning it and making it go through this media right here, and notice what happens now. It comes in, so he's still hitting it right here. He's calling out the degrees, by the way. I'm not going to look up. First 15 degrees. So see, you can see it refract right there at the end. I can't see the degrees, so that would be 30. So he's coming in at 55, and over here it's 25, right? Now notice now he covers a little bit of reflection right here. Now see it? Now notice this is getting brighter. See it? Now what happens when we hit what we call the critical angle? We get below, get what we call total reflections, and this is not a mirror. This is just a piece of glass. So above goes through and refracts. When it gets to what we call the critical angle, it will reflect. You'll see it? Let's keep getting brighter and brighter, and this over here is keeping white. And this is going to fix to hit critical angle or hit surface. Now this is gone. Now the light is what? It's reflected, bouncing off the surface. So this is what we refer to as total internal reflection. So if I can come over here and do that, so if I can come over here and do this surface and have a different type of glass or different types of plastic, it don't make any difference. And so what I have is I have an outside media that has a different refraction index and then I have an inside like this. If I shoot the beam in, what's going to happen, if it's below the, what we call the critical angle, instead of refracting through this, what's it going to do? It's going to bounce off. And then it's going to come over here, because here the angle of reflection is the angle of incidence, so it's going to come off at the right angle, and it's going to hit that side and do what? And then it's going to come over here and bounce, and now the light is moving down through that medium. And we'll look at this. We have a way to control this, and we'll talk about this later. So I'm drawing one light path. By the way, I'll just go ahead and get you. In fiber, we call a light path a mode. A mode, M-O-D-E. So we have two types of fiber. We have what we call multi-mode. What does that mean? Multiple paths that the light can travel through the core. And then we have single mode, which means, the core is so dang thin, it's so thin that it can't do anything else to flow down the center. There's only one path for light. And so we'll look at that. But what we're dealing with here is we're dealing with what we call total internal reflection. As long as I stay below this, what we call critical angle, then all the light travels down the center of the core, what we call a core. If I exceed that, then some of it's going to be refracted out through this other media right here, which we call the cladding, by the way. That's a G, not a P. And we call this, so it travels down the what? The core. Bounces off the cladding, travels down the core. And so this is the way fiber optics work. Which is pretty neat. They got a guy shooting water. It's really neat. So water can act like fiber optics. In fact, they do that. They've got some shows what they do where they actually shoot the light through the water. What's so nice, if they shoot a laser down there, you can literally see it doing what? Bouncing off the side. It's pretty neat. And they'll shoot that thing out in a stream, and it goes in an arc like that. And as far until it gets that turbulence out there at the end, that light follows it. It's really neat what they can do with that. It's called the refraction index. So what we're looking at, and this is not an important formula that you need to know. You need to know most tables use what we call a refraction index. So what we do is we have two things that we're going to deal with. Each one of them have to have a different refraction index for it to bounce off the side. And like I said, we see this all the time, in water. So you got air and you got water, right? You understand? So if you're back far enough and you're below the reflection and the water's clear, you get it bounce off and it looks just like a mirror because you're looking at it below the critical angle. Right? Have y'all seen that before? They'll have pictures where you got a really pretty smooth lake out there and you can't tell where the sky, you can't tell if the picture's upside down or right side up because everything back in the background is reflected off the light. Well, see, you got two media, right? You got air and you got water. The light travels faster in air than it does water, so you got two indexes, refraction indexes. And as long as and it has a critical angle, and as long as you're below that critical angle, then you get basically total reflection. But the closer you look, now you start getting refraction, right? You understand? And everybody that's had a fish aquarium or tried to fish, you see the fish there, and you throw your lure, and your lure misses the fish because you got that refraction index, right? I tried to fish with a bow one time. I was pretty good with a bow. I used to teach archery. I ain't shot in a long time, but I was never really good at fishing with a bow. And they buy those bows that they put out on their thing, but I didn't have one of those, so I had a big old long string. And I shot that thing one time and the string got wrapped around my arm. It tore my arm up. That arrow was
You might get to that level, those just bring for.
yeah. Well, you get refraction there too. So people sitting at different places. If you was right over the fish, you wouldn't get refraction, right? You understand? Because you're not hitting it at an angle. But if you're back off, so different people would see the fish at different places, depending on how big, depending on what angle they were at. So the angle of refraction. So if light moving through one material strikes a material with a lower refraction index below a certain angle, virtually all the light will be reflected back into the original material. At or above the critical angle, most of the light is refracted into the other material. And that's a really good thing. And so this is a pretty good example that everybody's seen. This water is not exactly smooth. Some of those lakes, especially out in the West out there, out in Colorado and stuff like that, they really get smooth with no wind. So we're above, up here we're above the critical angle. Or down here we're above the critical angle. Down here we're below. As long as you're below the, and there's my link to my video. Yeah, as long as you're below the critical angle, we get total reflection. If we're above the critical angle, then we start getting refraction. And how much refraction you get depends on how far above the critical angle you are. Now, when you're at 90 degrees, it's straight, right? You see it goes straight through. So, temperature, thermal behavior, when conductors are heated, resistance does what? Increases proportion to temperature. And I think I told you, we actually have a temperature measuring device we call an RTD. Resistive temperature device. It's just a bunch of turns of wire. Enough to get the wire enough resistance so we don't pull a lot of current. When insulators are heated, then what happens? Resistance lowers versus proportional temperature. So that's what we're going to see is that insulators are, one of the ratings of an insulator, of course, is the temperature they're designed to operate in. Did we look at this before? I guess, when heat goes up, the resistance insulator goes down. Treating is and this should be in your glossary, by the way. So what we did, especially since we don't have a textbook, if you look on the Blackboard and you look under course content and reference material, there should be a glossary in there. Whether you want to print that off, I don't know. I think you can read it. It says that this is being developed. So we'll pick up terms that's not in there, and I'll have to go back and put it in there. But it would be a really good place to study on tests because of all of these terms. So treating, what is treating? Yeah, due to mechanical or thermal stress. Surface moisture, when surface moisture and contamination goes up, surface current goes up. And we talked about surface current. We got three types of current flow in a conductor, that's an insulated conductor. You have the current that's flowing through the wire. Then you have what we call volumetric current, which is the current flowing through the insulator. And then surface current is basically set up by contamination, how contaminated the surface is. And of course, distilled water is an insulator. It's got a real high resistance, but very few of us see distilled water, right? You know what I'm saying? By the way, when you put water in your car battery, what should you put in it? Distilled water. Because you want the conduction to be controlled by the acid. And then plus over time, those impurities will break out of the water and get into the bottom of your battery. And eventually they'll short out your plates. We used to have a distilled water maker here in the chemistry lab, but it was nothing but a still. So you could have made moonshine in it, I guess. But it worked on the same technique. So they'd boil the water, and then they'd run it up to a pipe that was water cooled. So you turn the cold water on, and then it would distill it, and you'd get distilled water out of it. But it was basically a still. Tracking when current flows over the surface causes carbon form. Corona is illumination. So some of y'all didn't know what corona was. It's a luminous discharge caused by ionizing of air around a high voltage conductor.
Oh, I knew it for corona. Let's do that.
Yeah.
What's that?
The wrong plant.
Oh, you're talking about the...
Yeah.
That's what I was talking
With the
about.
line.
I'm not a drinker, but we did tour it. When we came back from Tennessee, we did go to the Jim Beam.
That's a good place to go.
Yeah. And of course, I should have took my wheelchair out there because I didn't get to tour all the big storage houses made out of wood, huge things. Barrels and barrels of whiskey out there.
I want that barrel.
Huh?
Like, I want that whole barrel.
But the other guys, went with us. Insulation resistance goes down. That's the one was coming back from Cincinnati. I'm sorry. We went by there. Insulation, resistance goes down as may cause what? 3. Of course, exposing these things to chemical and also to dirt. We got to be real cognitive of that causing the surface resistance of the wire to go down, right? So these are insulating temperature ratings. And I'll probably make this up. But we have polyethylene, which is PVC. Polyvinyl. Polyvinyl special. Polyethylene. Cross-linked polyethylene. EPR, I don't know if I did what that is. Polypropylene. Hyprovine. Silicon, Teflon, and Teflon TFE. We'd have to look at some of those codes. Luckily, when we look at insulators, and we'll look at this. Normally, when we look at insulators, they don't really tell you what they're made out of. They're usually made out of PVC or some form of plastic. And then when we get into jackets, so basically we're going to deal with two things. Normally what we're going to do, it depends on the conductor. Of course, we're going to have a conductor, and then it's going to be surrounded by an insulator. Now, what's the function of the insulator? The insulator is not the term insulator is not a protector. Now, it's just like, no, it's just like saying, what's the purpose of the walls of the pipe? Keep the water in there. So you got that push in there, and it's trying to push those electrons all over, right? So basically, that's what it is. It's to contain that pressure in there. That's what it is. Well, yes, but the current flow, you have to understand pressure. Yeah. We don't contain voltage. Voltage is a term. Remember, voltage don't move. So voltage is a what? It's a push. That's all it is, a push. Saying, contain the voltage, that'd be like it's there to contain my heart, right? So your blood vessels in there, what's the purpose of your blood vessels? It's not to contain your heart, which is the form of your pressure. It's in there to contain the blood. Now, when it flows, it creates a pressure, right? Or a push. It creates a force. and this force is pushing on the walls of the insulator, just like it would be in fluid. But the voltage itself is not actually doing what? The voltage source is not moving. That makes sense? Then what we do, and the insulator can do protection too, but the insulator, the main purpose of the insulator is to keep that push inside that wire, right? And then we're going to pick up another term called a jacket. Now the jacket is not an insulator. The function of the jacket is to protect, protection. Now sometimes, of course, the insulator and the jacket could be one and the same, where the insulator is actually given properties to help protect the wire. But in some situations, it's not. So a lot of cables, we have a separate jacket. So that thing that's around the outside is not an insulator of a cable. That is definitely a wire. I know what a true cable is. You know what a cable is. Huh? Not strands. A strand is an individual wire that forms a conductor. So we have two types of wires. We have solid strand wires and we have stranded wires. Then we'll come in and we'll encapsulate that in an insulator. It's pretty neat how they put those on there. The insulators are put on there by what they call extrusion, which is basically they just melt whatever they're going to put the insulator on there. They run the wire to the center and they're putting force on the outside, and the melted plastic just goes on there and it comes out a barrel on the end that forms what it's supposed to do. And then they'll run it through water to do what? To cool it down and also set the properties. And then they'll run it through a stenciling machine that actually puts the information about the conductor and the jacket on there. But a cable is defined as a group of conductors, of two or more conductors that share a common jacket, that's inside a common jacket. Now we also have, we're going to use the term tape cables for conductors whose protection is in multiple layers. So fiber optics, we got one conductor running through there, but we have what we call fiber optic cables, and they've only got one conductor. But the problem is they have multiple layers around that to help protect that fiber optic cable. So we'll have a plastic coating around the cladding itself. Then we'll have some Kevlar through there. Then sometimes we have what we call a pulling member where we can pull it with. Then we have an outside jacket. So we call those cables. High voltage cables, we'll have the conductor, we'll have a semiconductor layer, we'll have an insulator, we'll have another semiconductor layer. So we call those cables too, because the construction of the cable is in what? Multiple layers. So what we do is they identify cables by different coding, and it's not really important for you to know exactly what the insulator's made at. What you need to know is the environment that the insulator is designed to run in, right? So what they do is they'll come in and they'll put all types of codes on these things. So I'm going to look at, so what they do for the ampacity, I think we looked at this the other class, is they rate the American Wire Gauge rates cables according to their ampacity, their diameter and their ampacity. But the ampacity is given at a certain degree, like 20 degrees centigrade, right? You understand? And why, when they give the ampacity of a wire, should they give you at a temperature? Why should they do that? Well, the resistance of the wire changes with temperature, right? You understand? So anytime they give that, they're going to give, even in data sheets for solid state devices, when they give you that information, they're going to say it's at this temperature, because solid state devices change their characteristics with temperature. So we can't say, okay, what's this going to be here? What's that going to be there? So if you look at the ampacity of a conductor, if you look at the American wire gauge, it's going to be given at a what? It should be given at. It's just like compressors. One of the things that we rate compressors at is cubic feet per minute. How much volume of air can they move? Well, the problem is that the higher you get, that would go down. The lower you get, that would go down. So most compressors are labeled in what we call standard cubic feet per minute, which means the amount of air that compressor guarantees it would push at sea level. Well, see, now it means something to me. So now I have a correction factor where if I'm operating at 10,000 feet, I could take my standard cubic feet, I could multiply it by that, and then that would tell me what my compressor is actually delivering. Does that make sense? So anytime we deal with things like that, or these data sheets, what they're going to do is they're going to say, okay, this is at a certain temperature.
What about the SCFM?
What's that?
SCFM?
That's what I just got through. Standard cubic feet per minute. But that's the amount of flow that compressor could put out at sea level at a certain temperature.
Tools are right.
Yeah. Well, they have to. Because what happens is my compressor says, 50 CSFM, but if I go up 10,000 feet, it's not going to be able to deliver that. Right? You understand? Because the air is what? It's thinner. It's just like when we say boiling, Fahrenheit is 212 degrees, but that 212 degrees is at sea level. Right? You understand? That's what they have problems. They said, like on Mount Everest, is they get up there, their water boils, since air pressure is so low, the water boils at such a low temperature, they can't even make coffee. Because as soon as it boils, it turns into gas, right? You understand? Yeah, it's first problem. But if you was down where they have high pressure, where they below sea level, then it would boil at a temperature higher than 212. But most people don't know that. They say, what's the boiling temperature of water? And they say, what, 100 degrees centigrade or 212 degrees Fahrenheit. But they don't realize what? That varies with altitude. And we do have altitude charts, by the way. I think the hospital over here is listed to that, because they used to have a helicopter pad over there. And one thing they're very interested in when they fly a helicopter is the pressure, the temperature. So there's sometimes that they can't fly helicopters when it's extremely hot, or they have to really be careful because they don't get as much lift. And how did we get off on that? Who knows? So one of the charts that we'll look at is dang, I thought I just put that out there, guys. Is what we're going to do is we're going to code the insulator. I think this is a little more in next chapter. We'll go ahead and talk about it. So what they do when they build these cables or these conductors is they're going to stamp a code onto the outside of the cable, which tells you a lot of information. One thing, of course, is going to tell you your gauge. And usually they give you a temperature rating out there too, even though we can look that up. And then they're going to stamp a code on there. That indicates that tells you a lot of information about the insulators and the jacket. So these are the codes right here. So we have communication cables. We'll look at this later on, but these are the ones that are in the NEC ampacity chart. So we primarily in power, we use two types of insulation. We use what we call thermoset and thermoplastic. And so if it starts off with a T, it means it's what? Thermoplastic. If it starts off with an R, it means it's thermoset. And then the next thing we'll see like an H. So if you see an H, it means that insulation is rated at 75 degrees centigrade. Which is what, guys? Pretty warm. So what's the formula?
1.8.
Yeah, but really, if you understood the scales, so for every 9 marks on the Fahrenheit scale, minor marks, there's 5 marks on the centigrade scale. So if you took 9 and divided by 5, you come up and get 1.8. If you take 5 and divide it by 9, you get, I should know that. You get 0.555. So basically, that's the way I learned it. Is what you would do is you'd take the centigrade scale, which would be 75, and then what you'd multiply it by is multiply it by the conversion factor. So I'm going to say 9 divided by 5, which would be 1.8. And I'm going to close that up, and then I come up here and equals. And then what I would do is I compensate for the difference in the scales. So freezing in the Fahrenheit scale is 32. Freezing in the centigrade scale is 0. And it's nice to reference things to 0. So since I'm going to the Fahrenheit scale, I'm going to come up here and add 32 to this. So that means that insulation would be rated at 167 degrees Fahrenheit, right? And the other main rating we have is 90 degrees centigrade. So 90 degrees centigrade would be, I'm going to come up here and I'm going to go ahead and multiply by 1.8. And then I'm going to add 32 to that. So that would be almost 200 degrees. So almost the boiling temperature of water, right? So this is the two main ratings that we're going to run into in the National Electrical Code. So if it says HH, that's high temperature, right? Hot, hot. This is hot. This is hot, hot. If it's got an N out there, it means it's got a nylon jacket. R means it's thermoset insulation, thermoplastic. U means it's rated for what? Underground. W means it's wet or damp location.
No hot.
Yeah. No hot. Yeah. No hot. So the three temperature ratings, right? If it don't mean no, it don't mean it don't say no H. If it don't have an H, it's rated for 60 degrees. If it does have a H, it's rated for 75 degrees. If it has an HH, then it's rated for 90 degrees. And these are the only wires that's in the table for the NEC electrical code. And if it's got an X, then it's cross-linked polyethylene insulation, which I think was one of the charts that they did. I'd have to go back and look. By the way, thermal, and we'll look at the temperature. One of the insulations, the thermal set one of them has a real high temperature rating, but if you get it too hot, the insulation becomes brittle. It'll just peel off. The other one, if you get it too hot, then the outside insulation becomes plastic. It starts getting real soft. And that's the difference between thermoset and thermoplastic. Thermoplastic is probably the one that gets plastic, and thermoset is just looking at it, but don't write that down.
Not yet.
Not yet. So when I look at the actual code that we have, that NEC looks at, that we've already looked at, that we've already looked at the other day in the and this is on the website too. It's table 10-16, and I'll give y'all a copy of this, by the way. This is not a good version of it. In fact, I ran it off on my printer. Let's see if this is the one. This is actually out of the NEC book. No, that's got the wrong. Nope. Well, guys, I showed y'all that the other day. Didn't I? Oh, it's not 10-16 anymore. It's 10-15. So when they came out with a 50, I need to get rid of those. Oops. So this is 10-15. So if you was looking this up in the National Electrical Code book, then you'd look up code what? 310.15 in the new code book. And what they've done is the ampacity is dirated a lot. We talked about that the other day. But here across the top, what are these? What are those? Those are insulation types.
Yeah.
So those are insulation types. So TW, this is TW, which is primarily what we use in our house wiring. This can be run in damp locations, right? T means it's thermoset. Thermoplastic. T means thermoplastic. And wet or damp. These over here, RHW, this would be, this is rated at what? They're rating it at 75 degrees centigrade, which is 167. I believe that was right? Now notice they've got THHW, which is high temperature. Notice it's in two slots.
Yeah, but it's got a second. It's got a -2.
No, right here.
Yeah. Oh, wait. Oh, it's got it there.
Yeah. So what does that mean? That means we can use it in this application, or we could use it, in what? That one. So you'll see a lot of these repeat. THHN, what would that be? That would be a nylon jacket. XHHW, that would be cross-coupled. But these are these guys right here, right? Now notice over here, they give us two ratings right here. They give us AWG or what? We call that KC Mill. And we'll look at that in a second. Are we okay so far? Lost y'all? Now these are durations, and we'll talk about that later on. So these are worst case scenarios. And then it says, okay, based on the NEC here table, ambient temperature correction based on 30 degrees centigrade. So what they're saying is if it's above a rated, so if it's 60 degrees, right? Y'all understand that? Then these are dirating factors that we would come in, and if it's 10 degrees or less, then this would be, if it's above 60 degrees and it's 10 degrees or less, then you would do what? No, that's wrong. I need to go back. I think this is if it goes down, because each one of these. No, I need to research that a little more, guys. Just ignore me. This is if it's got multiple cables in the same that are in the same raceway. Because now you got multiple cables in the same raceway, and each one of them is generating heat, right? So this is a percentage. You got to be real careful. Percentage of the value. So that means if we got between 4 and 6 cables, we'd multiply the ampacity over here by 0.8. If we got 7 to 9, we'd multiply it by 0.7, right? You understand that?
Was there overkill or do that?
No, this is not overkill. This is what NEC recommends. You could go over that, but you don't need to go below that, right? But what you got to understand is the more you compensate for it, and this should take care of every situation that this conductor is rated in. I think we talked about that. So this number 14 gauge wire, if we look at an ampacity chart and we looked at a 14 gauge wire, a 14 gauge wire is rated at 32 amps. But that's in free air at a temperature of 20 degrees centigrade. But look what they rated here. So 14 gauge wire, what are they rated in? 15 amps. So why is it rated at 15 amps? That's more than half of the ampacity if we run it in free air and if we run it at 20 degrees. Well, what NEC has done is compensated or went ahead and dirated it enough to take care of any insulation that you would run into in the United States. Whether you live in Maine or whether you live in Arizona, if you run this within a house, 15 amps. So if you went out there in Arizona, a 15 amp service is going to run 14 gauge wire because they've already taken care of that worst case. So then they're saying, okay, if you do that, if you run it above 6, then this 0.40, this 80% is worst case. So that means if you use NEC code and you use the dirating factors, you will have no problem running this cable anywhere in any resident in the United States of America. Does that make sense? Oh, okay. So this explains it. I didn't look at the right column over here. So if you look at the right column, this gives you the ambient temperature. So what this is saying, if my ambient temperature is going to be in Alaska, well, Alaska's ambient temperature or average temperature is a lot less than our average temperature down here. So what that says is, it says if you're going to run it at 50 degrees Fahrenheit or less, then you can multiply this by 1.29. You see this, James? You can multiply this by 1.2. You can multiply it by 1.15. If you run it between a temperature of 51 to 59, you can get a little more, your ampacity would go up. 60 to 60, okay, so here it is right here. So our range is based on probably 25 degrees centigrade or right around there. Now, if you go above 78 degrees, then you're going to have to do what? You're going to have to start, then your multiplier is going to go less than what's rated over here. Y'all see what I'm talking about? Yes or no? Huh? So if you look over on the column, so if you run it at a colder temperature, you can get more current. If you run it at a hotter, so look over here, this gives you the temperature in Fahrenheit. So these guys are rated, basically, these ratings are worst case scenario if you run it right here. Between what? 78 and 86 degrees, even though it's rated at 75 degrees. So if you got this cable right here and your ambient temperature, your ambient temperature is in this range right here, then you actually can, so now if this is rated at 75 degrees, 15 amps, it's between this range right here. Let me get this out in a minute. You'll see what I'm talking about right here?
Yeah.
Well, if you operate it, if your ambient temperature is 50 degrees or less, then you can multiply 15 times 1.29. For this rating, you can multiply it by 1.2 if you're in the 75 degrees category. You can multiply it by this if you're in the what? 90 degrees category. And this holds true. So if you're operating at an ambient temperature below the rating, then you can actually up your ampacity. If you're operating above the rating, you'll have to start doing what? Taking it down. And where would you find in the National Weather Service gives you the average temperature of a location per year. It's on the national. I think it's National Weather. I know you can search it for it on the internet and say average temperature for a location, and it'll come up there and give you the average temperature of the location that you would have. So it means if I'm up at the North Pole, then definitely we would use one of these multipliers up here, right? That make sense now? Yeah, now it makes sense to me. I just didn't look at the right-hand column. Huh?
Average temperature on the pole is summer. -4.
Oh, you looked that up? You can find atmospheric pressure too. So if you wanted to figure out your cubic feet per minute, then you could find your altitude. Altitude, that's what you'd look at. I forgot where I found that one at. I need to go look that up. It was really neat. I think we was talking about compressors, the standard cubic feet per minute, and they gave you a correction factor when you actually do that, depending on your altitude. But now that would only come into play if you're really concerned with your flow, right? Now we can take a break. We're gonna. What are the two categories of electrical cables? How are low and medium voltage cables constructed? What types of material are used for electrical cable conductors, and what are their characteristics? What types of material are used for electrical cable insulators, and what are their characteristics? Of course, we've already looked at that a little bit, right? What types of material are used for cable jackets, and what are their characteristics? So what's the function of the jacket? So we need to split this up. So the function of the insulator is to keep the bush right inside water. Protect it from the environment, which include temperature and also would include chemical, underground rated cables and stuff like that. Power electrical and optical communication cables constructed, water, and I took the yellow out. I think when you get to that part, we'll skip over. Like I said, we got 4 whole units of optical fiber. What we're going to try to do here is concentrate on electrical right now. So the first chapter gave us a little feel of what we're going to get into the second 4 weeks. So we know that conductors provide 2 things. They provide what? Power or what? Communication. So we have communication cables and we have power cables. And like I said, sometimes we can communicate over power cables, but they're still designated as power cables. Power cables, of course, are going to be made out of metal that we see. And then we got communication cables. These are guys that we're going to send our information over, right? Electrical information over. And these are going to be metal or fiber. Are we okay? Pretty straightforward. Electrical power cables, application voltage, got to handle the load current, got to protect the environment in different ways that we're going to install these. That's my phone. You almost got to have a phone now. Nancy would go crazy. She'd probably come over. Probably. Electrical communication cables use many of the same construction techniques as power cable. Mainly we use copper, right? You understand. Communication cables or metal computer cables is we use a form of copper. It might be plated with something, or they might put an alloy into it, but these are going to be metals. And of course, the advantage of copper is it's the second best conductor of electrical current that we know of. The communication cables we'll look at, and we'll look at coaxial cables. So this is what we use in TV, using high frequency signals and high power applications. Twisted pair, the telephone cable uses it, or use this in networking. These are low frequency signals and low power applications. And then we have flat cable. What day? Is that, I mean, what day? Okay. Fiber optic cable used for communication only, right? Does not use metals, made of glass or plastic. These guys handle very high frequencies and they're impervious to EMI. What's EMI? Electromagnetic interference. Well, electrical motors, we got electromagnetic interference right here, right now. Because we have magnetic waves. Anytime we put current through a conductor and we don't shield it, it generates a magnetic wave. And we can pick it up. So I'm picking up an electromagnetic wave right now. Predominantly what frequency? Yeah, predominantly 60 hertz. So all I'm going to do on my oscilloscope is come up here and touch the leads. So I have this thing induced into me. Turn off this channel. Turn off this. And let me put my camera up. Now, of course, my scope is going too fast, so let me slow it down a little bit. And there you can go. You can start seeing me a little bit here. Let's change. Let's go to a lower voltage. So this is me. So this is electromagnetic induction, right? And this is 60 cycles. So the predominant magnetic waves we get here is 60 cycles. And we can use this, by the way, guys. I mean, we can trigger things like this screen right here. We have two methods touch screens work. Touch screens work off of pressure, or they work off of capacitance. This is what the capacitance is using right here. So when I touch my screen, it's picking this up right here. And then the screen is laid out in what we call a metric. So we have thousands of rows and columns. And then when it scans those rows and columns, it picks out where my finger's at. But this is what it picks up. And this is why when you get a stylus, this stylus right here won't work on my phone because it's not set up to work on that. So that touch screen on that one, on that HMI panel on the amateur line is resistive. So I can hit that sucker with anything. So I can hit my finger, I can take a piece of wood and hit it, and it works because what it does is it changes the resistance inside the metrics. But this is me, so this is EMI right here. Well, it's not interference, but this is electromagnetic induction is what it is. And like I said, if we didn't have that, our touch screen wouldn't work. So ampacity, do we understand what ampacity is? Ampacity, what's ampacity? Ampacity. Ampacity, it's the first one up there. What is ampacity? Exactly right. It's the capacity of a metal conductor to carry a current. So when we looked at these different ratings over there, that's the ampacity rating of a current. Anneal, does anybody know what that means? We're going to go back and look at this, but anneal, a buffer, does anybody know what buffer means? We'll look at it. Well, not really. A buffer is a go-between. So in digital, we have a device. We call them buffers. They don't do anything to the logic. So a high end will give me a high out, and a low end will give me a low out. But they have a reason. So it's a buffer. It's a go-between. So that's the same thing. Characteristics, impedance, and everybody know what that means. Now my watch is working. I mean, it's picking up my phone now. Circular mill, cladding. I don't know why coated wire is in there. Core, DB in communication cables. You've got to understand. But what is it? Originally, it was set up as a measure of sound, but we use it for all types of things. We use dB in communication basically the way we use the engineering notation. So dB is a method that we can represent extremely large and extremely small numbers with very few digits. And it usually deals with gains and it deals with attenuation. So we'll say this thing has a certain dB dB loss. So when we measure our fiber optics, it has nothing to do with sound. We're measuring light. But the amount of loss you can have in a dB in a cable is rated in dB. But originally, you're exactly right. It was set up for sound. Yeah, you'll see that a lot, but you'll see it a lot in dielectric constant, ductile, extrude. We've already talked about that. Home drawn and hydroscopic. We'll look at those terms. And these all should be in that glossary if y'all have access to that. So everybody okay for solid? So this is some electrical conductors. We have solid and we have strand. Now this would truly be a cable, right? Now why is it truly a cable? Inside a jacket. Yeah. So these are some of the terminology we'll run into. Stranded. Everybody okay with stranded? What does that mean? It means the wire consists of multiple strands. I think the definition says wound, but they're not. We have straight stranded cables, or straight stranded conductors, and we have twisted stranded conductors. Straight, yeah, and the ones that's on the problem with straight is they have a tendency to birdcage. What's birdcaging? Well, they want to spread out, yeah, where the conductors want to spread out. So straight, yeah, spreads out more. twisted, don't bird cage as much. Soft drawn. So so hard drawn means it's drawn through a die after it's what? Cool. So how do we set the gauge of a wire? Well, normally what they do is they start out with a big chunk of copper, and they start off with copper rods, and then they start doing something to stretch it out. But they heat it up, get it hot, and then that's one way. Hard drawn means you just lubricate the heck out of your dies and you pull it through the die. And when it goes to and this is done a lot because it's cheap. So all you got to do is just keep your dies in good shape, right? You understand? Change them out. If I soft draw it, then what would I have to do? I would have to do what? I have to heat it up, and that's money, right? And then I have to pull it through a die. So you see a lot of metals, they change the gauge. They go to a smaller gauge, smaller size. And you have to understand, gauge numbers, these are numbers assigned to a gauge. So when I say a smaller gauge wire, I'm not talking about the number, I'm talking about the size of the wire, right? You understand? So when I say a smaller gauge, it means a smaller wire. But a smaller wire would have a bigger number. You understand that? It gives people a problem. So the advantage of this is it's hard drawn, it has high tensile strength, it has a low elongation under stress. And this is another thing we have to consider is that we have different cables, we have different wires that we call them riser wires. These guys have the ability to go up a wall. And what happens when I start pulling cables up a wall, then the weight of the cable is pulling down, right? And the longer that rise is, the more stress it's going to put on the cable. Well, what happens when you start putting stress on things? Well, they're going to stretch them for one. It's going to stretch before it breaks. What happens if a wire stretches? You change the gauge of the wire. If you change the gauge of the wire, you change its what? You change its ampacity. So we have wires that are hard drawn. So hard drawn wires, these would probably be the wires that are designed to run up a wall without being supported. We can't do that with house wire. So if you're in the house wire and you see they staple that stuff all over the place, you have to have a staple over so many inches. Because you run that up a wall and it's not hard drawn, it's soft drawn, right, or heated, then what's going to happen? It could do what? It could elongate and it could stretch. So anybody ever do any house wiring? Right.
Yes.
Well, what you do, you get inside those walls. Those wires just don't run up those walls. Though in that wall, they'll be over on a 2x4 and they'll be stapled every so many inches. And well, I think it's within. It's been a long time since I taught the class. So you got to have a staple so many inches, and then you got to have a staple so many inches up when you put into a pull box. So then we have soft drawn. These guys are heated and cooled. We heat them up, then we cool them, then we cool them down to remove stress. By the way, this is also called annealing. So when you have annealed copper, what it does is it makes copper softer. Softens the metal, low tensile strength, high elongation under stress, usually used indoors. So just about all your communication cables are going to be soft drawn. Stranded. Multiple solid strands twisted together. I need to go back and pull that out. They're not really twisted. Some of them are not twisted together. So we have straight strands and we have twisted strands. And what advantage would the twisted? What advantage would the straight be over the twisted? So which one would be cheaper? Straight, stranded, or wire? Well, if you twist them together, automatically you increase the length, right? So you have to have, anytime you twist, Anytime you take something, you start twisting, what happens to the length? It goes down. It reduces, which means I would have to have more wire to cover the same amount of territory. So what advantage does twisted have over stranded? Huh? Now, what advantage does it have? It's going to be stronger, right? You understand? Because your wires are closer together. So when you do the twist, it takes more copper, but the cable itself is stronger. And plus it doesn't do what we call bird cages much. Less susceptible to scribing. What do you think we mean by scribing?
Scribing is where you're kind of slightly cutting the strand.
Yeah, it's when we put a perpendicular notch or nick into a solid. So that would be a little scribe right there. But what happens if you ever cut glass is pretty hard. But how do you cut it? You scribe it. All you do is you take what they call a glass cutter, but it shouldn't be called a glass cutter, it should be called a glass scriber, because it does not cut the glass. It just puts a perpendicular niche into the thing, and then you put it across the surface and you push down on both sides and it'll break right down that scribe. So what happens if we scribe a strand? Breaks a lot. Well, if you bend it, it's going to do what? It's going to break. And normally, when do we scribe it? When would be when we scribe it? When would it most likely be scribed? When you strip off that insulation. If you don't strip off that insulation correctly. So you never want your blade to touch the conductor at a right angle. Now we can hit it like this. So I can bring my blade in like that and hit it. So here it's going to put a little nipple in it, right? A little indentation. So you ever seen electricians strip with knife? They don't strip it like this. They strip it like that. And then that way, if they do hit the wire, it's not going to scribe it. It's going to just put a little dent in it, right? You understand? So anytime you strip with a knife, don't. And you see people do it all the time. If I ever walked into a house and I saw an electrician put that thing on his finger and put that knife like that and take that knife and do like that. Now the problem is it's going to work for a little while, but inside your walls, those cables are constantly doing what? They're expanding and contracting, and eventually it will break. Of course, the big advantage of stranded, what's the big advantage of stranded over solid? Flexibility. That's the big advantage. What's the big advantage of solid over stranded? But that's not necessarily an advantage. The advantage is it's easy to terminate splice. So we get a solid strand wire. You'll see people just twist those suckers together, cover them with tape, or they'll use what we call a wire nut, which we'll look at. They'll put it under a screw. They'll wrap it around the screw. They'll tighten the screw down. Of course, we already know this, right? Silver, best conductor, used as a plating on contacts, used as a plating on some conductors. And we do have a solder, by the way, that they call silver solder. It's not silver, it's silver solder, which is a 6236 thing. So a silver solder would have a lot less resistance than regular tin lead solder. Now the ratio of silver solder they use in brazing. So in compressors they use a silver solder too. Now what other metals in there or not, I don't know. Why? Because it's got a stronger strength than regular tin lead or other solders. We don't use silver solders in water pipes. We use lead-free solder in water pipes. Very expensive. And of course, the second best conductor is what? Copper. And and multiply. Now, we used to use a lot of aluminum because it was so much cheaper. And the rule of thumb is if you were going to go from copper, so if you're using 14 gauge copper, if you went to aluminum, you would use 12 gauge. So they say the rule of thumb was to go up 1 gauge number. But they was putting that stuff in houses. My son's house has got aluminum wiring. Trailers, they use a lot of trailers. They use a lot of aluminum wire. Now, what's the problem with aluminum? But that's basically aluminum is illegal to use in housing and also for commercial applications. So what's the problem do we have with aluminum? Well, copper does too. Oxidizes. So copper, aluminum has a real high coefficient of expansion, which means it does what? What does metals do when you heat them up? Expand. What happens when they cool down? Okay, so that means it's hard to keep these things tight. They automatically try to wiggle themselves out of whatever we put them in. Another thing is they oxidize extremely bad. Aluminum oxide or aluminum rust is a really good insulator. So that means if we're going to use aluminum, we're going to really cinch these guys down. We're going to put them down real high. And then you put an antioxidant coating on any exposed wire that's going to be in something. So if you're going to splice aluminum, you put that antioxidant around it, and then you splice it together. And you really do what? You really crimp it down. So you don't want to terminate this without putting that stuff on there. And you never want to mix copper with aluminum without putting antioxidant on it, because those are two dissimilar metals and they will break each other down. I've got a copper, by the way. I've got a thing in there. I'll go find it when we take our next break, where a guy whoever did this, crimped an aluminum conductor and a copper conductor together without putting that without putting that oxidation agent. And you can buy that stuff down at Lowe's, by the way. You can buy it. We have to do it because even though they drop copper wire down from our house, the neutral or the ground that they run down is aluminum. And when they splice that into your house, they're going to have to splice it to what? Copper. And by the way, in fact, come to think about it, down drops are using aluminum too. But if you ever went up there and took all that tape off, you'd see there's a brown goop all over everything, and that's that oxidant, so it don't oxide. So never mix copper with aluminum without putting that stuff on there. Well, what my son does is they still sell aluminum outlets, by the way, because there were so many houses and stuff built with aluminum. They caused so many fires. What people would do, even electricians didn't know that. So they'd go to Lowe's and buy all these copper receptacles, right? And then they'd come in and hook it into their aluminum wiring, and then their house would burn down after a while. Third best gold, fourth aluminum, strong, light, and cheap, using high voltage transmission lines, used for power distribution, materialistically used on most integrated circuits. Gold, the big advantage of gold is we don't use gold as a conductor, but we use it as a plating. For a long, long time, people say, well, why can't you melt that gold off there? Well, the problem is, you can make money off this if you do it in extremely high quantities. But normally what it means, if you melt it off, it uses more energy to get the gold off by melting than it does than you'd make off of it. Other conductors, brass, zinc, iron, and nickel. Mercury, which is a metal. Then we do some wires as conductors, But really calling them conductors is not exactly right. They're actually resistors. So we use a lot of tungsten inside lights because it has a pretty high resistance. And then we use nichrome. These are used in heaters. So calling these conductors is not exactly true. They're actually resistors. And if we push current through a resistance, then we get a voltage drop, but also we get I square R, right? We get heat. And so these are the advantages. Copper is what? Highly conductive, inconspicuous, ductile, and malleable. We can move it around and resist the corrosion compared to silver. Now, copper oxidizes, but it don't oxidize as fast as aluminum, and it doesn't oxidize or rust as fast as aluminum. Aluminum is cheap and light, does not get along with copper, corrodes and expands and cracks with temperature. So it's real hard to keep these things. We don't put these things under screws. You almost never now see aluminum under a screw. Because what will happen? It'll come loose. And this is the big problem they had in houses. You'll see it in compression splices. You'll see it crimp down and stuff like that. Combination of metals. These are called alloys. We mix copper with other metals to improve its characteristics. Silver and gold, we use those as what? Plating. Yeah, so they'll take copper and they'll combine it with nickel. Nickel's but nickel has a real low corrosion rate. And of course, we already talked about this. So what determines the resistance of a conductor? That sounds like a good test. Let's start down. First of all, we look at the material. Then we look at the size. Then we look at the length. And then we look at the temperature. Even though you literally can give them in the order. That's the way I like to give them. So the material the conductor is made from, the size of the conductor, which is the area, by the way. So the American wire gauge is for round wire. The problem is a lot of our conductors are not round. They're flat, especially on printed circuit boards. Some waveguides are not flat. So what we would need to do is we'd need to take that round wire and convert it into an area. Does that make sense? So any conductor with the same area would have what? The same ampacity. Right? So how do we determine the area of a circle? 2 pi times the radius, right? And then, of course, of a rectangle, it would be the length times the width. And then of a square, it's any side square. But length times the width works on it both. And the ambient temperature. So what's ambient? Surrounding. Ambient is surrounding. So right now, in here, it could be whatever it is. But I get inside this guy right here, that's not room temperature, it's at a different temperature. Surrounding inside this, right? So it would have a different ambient temperature. So when we talk about the conductor, when we talk about the resistance or the rating of these insulators, it's not the room temperature, it's the ambient temperature. So if I had a black insulator running out across my ceiling up there, then it would be at a higher temperature than the temperature for the day, right? You understand? Anybody got a black car or a dark car? What about your motorcycle?
Oh,
yeah, my riding lawnmower's got a black seat on it. And boy, I'll get off that thing and I'll come back and it's so hot. So ambient is the surrounding temperature. What temperature is surrounding or at that cable or that conductor or whatever we're talking about. American wire gauge. We already talked about this. Everybody else going to hear size and number values of the conductor's diameter. The larger the number, the smaller the physical size. We do have, and by the way, somebody took our American wire gauge. So we had a couple American wire gauges around here, and now they're both gone, and we have a hard time finding these. So American wire gauge basically has got a bunch of little holes cut into it. And what you do is you just take the conductor and slide it in. And it should slide against the sides, and that would, then you can come back and do what? Read the gauge number. The American wire gauge doesn't give you the diameter, and that's not exactly true. If I remember ours, if you flipped it over, it gave you the diameter on the other side. So this is the portion of the American wire gauge that gives us the diameter of the wire. It gives them to us in inches, which we're primarily going to use. And it also gives us to us in millimeters. So we have two standard wire gauges. We have the European wire gauge, and then we have the American wire gauge. The American wire gauge used to be exclusively in inches. But guess what they've done now? They've got the millimeters over there too. So we'll look at both these. So that means I need to understand both these. By the way, the American wire gauge goes down to about 50. And that would be the smallest size. And then it goes up to what we call 4/0, which would be the largest size, represented in the American wire gauge. Above that, we're going to talk about what they call circular mills. And that's important to know too. Huh? Where? Oh, okay. Oh, you said we was. I thought you said I was. And I said, I don't remember. This is the actual formula. This is just nice to know. And how they came up with this, I have no idea. And who came up with this, I have no idea. I think the rule was if each gauge number doubled the ampacity or something like that, but I can't remember. This is the formula they came up with. Where we get the gauge number, we take the diameter, this stuff over here. So a circular mill and a square mill, unfortunately, we'll run into both of these. Huh? Yes. We run into square wire a lot. So all the wires inside this are square. Well, they're not really square, they're rectangular. So all the wires on a printed circuit board are not round.
Oh,
Yeah, that's what we call the traces of bolts. Now, when I use a trace, it's got an ampacity rating on it also, right? And my ultimate goal is to, if I'm good, my ultimate goal is to use the smallest gauge wire I possibly can for my application. And why is that? Yeah. So the smaller the gauge wire, if it's made out of copper, when you sell copper, they sell it per pound. So the bigger the gauge wire is, you're not going to get any more amps than what's available in the circuit.
Yeah.
So I could come in my house and I could run 12 gauge wire all over the place. I could use 20 amp receptacles all over the place, which is what we have here, by the way. But what did I just do? Yeah, and if I'm never, ever, ever, ever going to run a device that requires 20 amps, then I've just wasted a ton of money. But it'd be nice. We could run 20 amp. So you can see a 20 amp receptacle. they'll have a cord. We'll come up with a method. Well, the problem is there was no standard. So it means they'd come in and they'd put one manufacturer's plug in my house, and then when I wanted to buy a cord, I would have to find that plug, right? You understand? So what they did with NEMA now is NEMA has standardized all this plug. So I can go out and buy a NEMA 15. I can go out and buy a NEMA 15R, and anybody that makes a NEMA 15P would do what? Would plug in there, which now it makes it so much better. We have NEMA is basically over here. I don't know about Europe. It's a real Europe standards are completely different. They use a different standard.
Yeah, this was
No, they're Europe. They're circles. So they're circles.
oh, I thought they had some.
Well, they do. It depends on where you're at in Europe, and that's a problem you have. I'll bring my thing in. So when we was going over there, and they run 240, they don't have a low voltage. All they got is 240 over there. You know. So you can buy adapters, or you can buy one that converts it back over to 115 volts. It's got a transformer in there. I'm not going to tell you what I did. I burned up my toothbrush over there.
You burned under?
No, I didn't burn up my toothbrush. I burned my charger for my toothbrush.
Oh,
But it was my fault. Because you have to switch the voltage on the side of the thing, and I didn't switch it. So I put 240 across my toothbrush charger. But that's okay. I got my own. That's one thing about it, knowing a bunch of stuff like this. You can help sometimes. I'm going to show you a video too. I need to show y'all that. Don't get a laugh. It's about this guy that's putting up YouTube videos, and he's supposedly trying to show people how to do stuff.
oh wait, is
Huh?
you go by the
I don't remember. He should. It's hilarious. So circular mills, the area around the conductor that has a diameter of 1 milli. So we rate so circular mills would mean if you got 2 circular mills, it would be 2 inches, right? 3 circular mills would be 4. It's not really an area. We'll look at that in a minute. Three basic conductor shapes. Are you okay there? So they're square, round, or rectangular. The area of a rectangle is the length times the width. And then the convert. Let me go ahead and bring these up. What we're going to use in this class, and it's up to you. So what we do is, so the American wire gauge is based on what? A circle. But I'm trying to figure out the ampacity of this. So what sets the ampacity is the area that's available for the current to flow through. So if I had a method of taking this and converting it over to area, then I could use this that had the what? The same what? Area. So the formula for area of a circle is equal to pi, which normally we use 3.14, times the radius squared. And what's the radius of a circle? So a line that touches both sides and crosses to the center, we call that diameter, right? And what's the radius? Well, the radius is 1/2 of the diameter. So the problem we have, it's not a big problem, is that I could do it. I could say, okay, they give me this diameter, I could divide it by 2, and then I could go ahead and I could do the math. By the way, how did they come up with pi? Y'all should know. Some of y'all have taken my classes before. So how did they come up with pi? Well, it's the area of a circle. We use it for a lot of things, but pi is if they was to take a string and run it around this circumference right here, and my circle's not a good one. And then they took the length of the diameter, and they took the circumference, and they divide it by the diameter. It will always equal pi. Always. So it's the ratio of the circumference of a circle to a diameter. And what's unique about pi, it is a unreal number. I mean, it goes on for how long? Yeah, we don't know. So usually for pi, we use 3.14, we use 3.14159, and that's the farthest that I've ever carried it out to. Your calculator carries it out to 13 digits. Most calculators do. Most calculators display 10 digits, but they calculate 13. And they calculate 13 so the calculator can round correctly when it starts rounding. And it's got to do that a lot when it jumps into scientific notation. But when we get our American wire gauge, the American wire gauge gives us the diameter. So we could take this equation right here and we could convert it over to say the area would be equal to pi times the diameter squared, and then I can divide that by 2, and that would give me the same answer, right? Everybody understand that? Are we okay? No, I'm sorry. The diameter squared divided by, let me redo this. That's wrong. It's going to be the diameter divided by 2 squared. That's a big difference, right? That would give us the same answer. Well, I could come up here and I can say, well, the area would be equal to pi times the diameter squared divided by 4. So what did I do? I just took care of that guy right there. We follow this? Everybody okay so far? Or I could do a little math and I could pull my diameter square out, and then I can say pi divided by 4. Because what I can do is I can go ahead and take pi and divide it by 4. So on my calculator, if I take pi, and I'm going to use 3.14, and I divide it by 4, I come up and get 0.785. Y'all follow me so far? So normally what people learn, if you looked this up, they'd say, okay, I can do all that math, or I could just take the diameter squared times 0.785. And that's where the 0.785 comes from right there. So you'll see a lot of equations, instead of using pi or rad, pi times the radius squared, then they'll say the diameter squared times 0.785. So what would be the equivalent area of a circle that had a diameter that had I don't know what that question's at. That don't make sense. A circle with an area of 0.0818, what will be its equivalent square area? So, looks like that's the answer to me. Aren't you? So what should the question be? What should the question be? Yeah, so what I'm saying is that, the way it should be worded, and these are my slides. I can't blame anybody for this. What wire has that? That's okay. This would be inches. We use that to represent inches. Use this to represent inches. What would that be? Don't know. I ain't doing it. So you just took that and multiplied by 0.785? Yes?
That's already the diameter.
No, what we're doing is finding the equivalent square. What is the equivalent square area? So I changed it up a little bit. So a circle has a diameter of 0. And then we multiply that by what? 0.785. Okay, there we go. So if we looked at the American wire gauges, which I should bring up, did I have that here? Okay. So this guy right here has a diameter, so a 14 gauge wire has a diameter of 1.63 inches. So what would be the equivalent square area? I don't have my calculator here.
That's what?
1.63. Then all we have to do is just multiply that by 0.785, right?
0.8.
Huh?
Multiply by 8.
0.785. So they're carrying these out to 2 digits, so we are to at least do that, right? Yeah. And that would be square area, right? You understand? So that means if I had a rectangular conductor, then I could either change the height or the width to get the same in passing. All that makes sense? I'm glad you. We have two methods of representing conductor sizes. We have what we call the American wire gauge number, and then we have what we call circular mills. And both of them will give an indication of the diameter of the conductor, right? Everybody okay so far? Mill, pronounced mill, is a short, it's short for metric prefix milli, and is equal to 0.001 or times 10 to the third. Are we okay? To the minus third, I'm sorry. To go from diameter to mills, we multiply the number by 1,000. Is everybody okay? So 14 gauge wire has 1.63 inches. This is the diameter. So how many mills would that be? Well, back in intro, you learned that all I have to do to go from units to mills is just come over here and grab that decimal point and move it over 3 spaces. And this would be in mills. Are we okay so far? A circular mill is a cross-sectional area of the conductor that has a diameter of 0.001 inches. Now this is just nice to know. We're gonna bring this together in a minute. A square mill is a mill area of a square with its sides at equal to 0.001 inches or 1 mil. So we already talked about this. Circular mill cross-sectional area is nothing but, so we have a term we call circular mill. Circular mill. So to calculate circular mill, all we do is what? And the second one, I've never seen that used. So we call these circular mills. Now this is what you need to know. So what is circular mills? All we do is it's the diameter what? Squared. Everybody okay? Times 1,000. But what we're going to do is we're going to figure out we're not going to use 1,000. We're going to leave it alone. Everybody okay? That makes sense? Okay. Now this is where it's going to kind of get you confused, because back in electronics, we learned when we go to a K, we move it to the right 3 times. I mean, or to the left 3 times. But what we're doing is we're starting out with a mill. A mill is 0.0001 milli, right? You understand? If I take that and multiply it by 1,000, I come up and get the same number that I started off with. Are we okay? So I got 1.63. Everybody okay? Then I'm going to square that. What does that come up and give us? What we got? What's that? 2.67. Huh? What's that? 2.66. Are we okay? You got any problems with that? Huh? What's that? Then so that would be the number of circular mills, right? Everybody okay? Then what we do, then what they do is they multiply this times 1,000. What would that give me? No, this is not right. I'm doing something wrong. To convert to decimal fraction into KC mills, this is what we this is what we're going to do. KC mills. We multiply the fraction by what? Requires the point of the fraction to be moved to the right 3 times. Now this is what's so confusing about this. So I came up and got what back here? 2.66, right? Huh? Okay, that's right. So we're doing something wrong. And I already know this, guys. I'm sorry. So what's a okay, that's millimeters. My fault. That's it. That's the problem. So So I was looking at the wrong column. I should have known that. So this is the diameter of a 14 gauge wire. What's that? 0.0 or 64.1 million inches. At least I knew I was doing something wrong, right? Okay. Now, what we're going to do now is we're going to square that. And what does that come up and give us? When we square this, we're multiplying a fraction times a fraction. So anytime you, what'd you say? Maybe you said it right. Okay. So 4.1 milli. Is that right? Which looks like it can be right. Don't understand. So if you multiply by a fraction, you end up with a smaller number than you start off with. So we're taking a fraction, multiplying it by a fraction, so we should expect a smaller number, right? You understand? So this looks like it could be right. Now what we do now, y'all understand, is we move this to the right 3 times. 1, 2, 3. Are we okay? So we would use this term right here. Now remember, a mil is 0.1. This is what people don't understand. Because back in DC, we learned if I got a real big number, I move it to the right, and then I call it K. But you have to remember, this is mils. Mils is already a milli, right? You understand that? So if I came over here and moved this back to the left, I'm not getting a whole number. I'm still getting mils, right? You understand what I'm saying? Yes or no? So what we're saying is that we can either wire. So how do we do KC mils? So a KC mil is we take the diameter and we do what? Square it, and then we multiply it times 1,000. Move it to the right 3 times, and then we say KC mils. Now the problem we have is the American wire gauge only goes up to 4/0. So any wire above a 4/0 is going to be in KC mils. If we did that right. So this is wrong because I was using what? I was using millimeter. So what would 0.135 be in KC mils? Just move it over, so that'd be what? 135, right? And this right here would be what? 37. Are we okay? I did this wrong a while ago. I did this wrong a while ago too, because I'm sorry guys. I'll get this right in a minute. So when we take, what was the diameter of that thing? It was, not this guy, not this guy, not this guy. So 14 gauge was what? So 14 gauge. Okay. So this is, so guys, I'll get this right in a minute. Okay, so we're ready. This is going to be right. So first of all, let's figure out the KC Mills of a 14 gauge wire. So what I'm going to do is I'm going to come over here. I'm going to come over here, right here. So here's 14 gauge wire. If you can't see it, it's 0.0641. Let's don't do mils. Let's don't do milli anything right now, because that's what's getting us confused. I'm gonna square this. So let's don't go milli. Let's just give me the fraction, because we're ended up with a lot bigger numbers than we're supposed to have. So give me the fraction when you square that, 0.0641. And the problem we have is we use engineering so often that it got us screwed up there. So what would that be? 0.0641 squared. What's that going to give me? .0041. Does it go out further than that?
0.18.
Okay, so this is good.
Oh, yeah.
Then I'm going to take this number, and move it to the right 3 times. 1, 2, 3. 4.1 KC Mills. Yeah, we was coming up with a huge number for a 14 gauge wire. And notice, so what we do is we use the American wire gauge for any gauge up to 4/0. You understand that? Then after that, they start specifying the wires in KC Mills. Everybody understand that? There's not a 5/0.
So, what you would consider a 5/0?
Like 250 KC Mills.
Okay.
And of course you say, okay, 250 KC Mills, what size is that? Well, 250 KC Mills, guys, all you have to do is take the square root of it, right? You understand that? You divide it by 1,000.
You can tell what all these is in that kind of wire.
You're going to be, because, well, that's not, I'd imagine Revere would probably have some stuff on there that's got more than a 4/0 wire. Because a 4/0 is right around, it's a little smaller than a 1/2 inch.
Yeah.
460 millimeters. Y'all don't have any wires up there bigger than that? What's that?
First jobs, they put me on at 3/0, and they're trying to get a little guy like me in 3/0.
It was stranded too. Most of your wires that big are stranded.
Yeah.
Because if it was a solid piece, you wouldn't have been.
No, that's big strands. Those strands.
So I'm going to divide this by 1,000. And then I'm going to take the square root of that. Oh, I did. Yeah, I did 250. I'm going to divide that by 1,000. Yeah, and then we're going to take the square root of that. I'm still doing something wrong there. Huh? 0.5? That's what it's supposed to be, because you look, the biggest thing we got is 0.46. So I did that something. So that means should be bigger. It should have a bigger diameter than 0.46. So 250 millimeter would be a half-inch cable. Would be half inch. Okay, let's take a break.